Alright, in this lecture, we want to talk about qualitative response models. A qualitative response model is where the dependent variable is qualitative in nature. It is not quantitative, alright, but rather it is qualitative in nature. When we talk about qualitative variable, it can either be nominal variable or ordinal or a ranking variable. A nominal variable example will be, let's say, the color preference. So you can have blue, yellow, orange, green, or whatever have you. Or it can be, for instance, whether to purchase a house or not to purchase a house. So the variable is either yes or no. Ordinal variable will also be qualitative in nature, but it is ranking in nature. For instance, the level of agreement. So strongly disagree, agree, or very much in agreement, for instance. Okay. Now, in this course, we are going to focus on nominal variables. The dependent variable is nominal in nature, and we're going to further focus it for only those with two possible outcomes. All right, so it can be, let's say, yes or no, or it can be success or failure, or whatever have you. Okay. So the dependent variable in this course that we will talk about is a binary variable. All right, binary means there's only two, or dichotomous, just one or two. Okay, just either this or that. So when the dependent variable is quantitative in nature, as what we have learned before, all right, the objective is to estimate the mean or the expected value of the dependent variable. So if you have your regression equation like this, so we would be interested to find the expected value of the dependent variable given the values of your explanatory variables. So we would be interested to find this. However, all right, when the dependent variable is qualitative binary variable, as what we are going to talk about in this lecture, the objective is to estimate the probability of the dependent variable outcome being a yes or being a success or being having the value of later on we will put the value as either 1 or 0. So basically we're interested to find the probability of the dependent variable assuming the value of 1, or alternatively assuming the value of 0, right? Therefore, when we are dealing with qualitative response model, we are dealing with models which are known as probability models. Okay, in this course, we are going to look at three types of probability models, which would be first one, your linear probability model, or in short, we call it as LPM, logit model or logistic model, and probit model or normit model. Okay, so here, as we said before, the dependent variable will assume the value of either 1 or 0. Okay, so just recall that in your statistics class, when we find the expected value of a variable, if it is discrete in nature, then it is just the summation of a possible value of that variable times by the probability that that variable takes on that value. Okay, so you sum it up and you will get the expected value of A, basically the mean value of A. All right, essentially this is your weighted mean, weighted by the probabilities. So in our case, all right, the expected value of y, because y will take on either 1 or 0, is going to be 1 times the probability that y equals to 1, all right, 1 times the probability of y equals to 1, plus 0, all right, times by the probability of y equals to 0. Because this is 0 times this is gone. So basically the expected value of y is just this term, which is the probability of y equals to 1. Okay, for the linear probability model, we have the probability of y equals to 1, all right, is equal to the expected value of y for given values of your explanatory variables, and it is just equal to beta naught plus beta 1 x1 and plus until beta 1 x beta k sk. Okay, so you will find that the way that it is written is similar to the ones that we have seen before when the dependent variable is quantitative in nature, right? So this is why we call it linear probability model. Okay, so you have over here. However, we have problems with the LPM, all right? Number one is that the variance of the error term is heteroscedastic. So when you have this error term over here, it is heteroscedastic. The value will change when the axis values, all right, the explanatory variables values change, then the variance of the error term will also change. Okay, so just very quickly, if we look at the variance of error term, it's the same as the variance of y, and variance of y, right, formula wise, is just expected value of y squared minus the square of the expected value of y, right? Now, here we can just use the previous formula that we have before. When you solve this, all right, you will end up with variance of y is just probability of y equals to 1 times probability of y equals to 0. And this would be the same as the variance of u, right? So the variance of u is the probability of y equals to 1 times probability of y equals to 0. And this value, all right, is not constant, all right? If it is homoscedastic, this will just whole thing here will be constant. But this is not constant because you find that the probability of y is given as such whenever the x sum or all of these x's values change, then this number will change, all right? Similarly, this value is just 1 minus probability of y equals to 1. So the numbers are not constant. When this is not constant, the variance of u is not constant, so you have a problem of heteroscedasticity. Okay. Now, more importantly, the second problem is that the probability values are not constrained between the values of 0 and 1. Because this is probability value, you would want it to be between 0 and 1 because it's a probability value. But you know that this term here, all right, on the right hand side, okay, all these things, it can be, all right, not necessary between 0 and 1. It can be negative and it can also be greater than 1, right? So we have a problem when we want to model, all right, this to be a probability model. Now you find that in this case over here, these values are not constrained between 0 and 1. Okay. Another problem with LPM is that it assumes that the marginal impact of X on the probability of success, in this case, success can be anything, all right? Success can be, not able to, purchase a house, or for instance, or able to purchase a house, whatever, what you want to, define this success to be. But in this case, when you model it as a linear probability model, it is assumed that the impact of X, all right, on the probability of Y equals to 1 is the same for all X. So for instance, if we talk about, let's say, probability of y equals to 1 is probability of purchasing a house, and this is a function of income, all right, the linear probability model assume that, the relationship is linear, all right? So this with a slope of your beta, one of this beta, if this is income, so this is the slope with a slope of beta 1. All right, so it is assumed it is like this. In other words, all right, the increment in the probability of purchasing a house is the same, all right, for any level of income, which is, quite unrealistic because when you have very low income, all right, the probability of purchasing a house, right, the increment is very, very insignificant. But when you arrive, at a certain level of income, all right, so you will find that if your income is, let's say, 4,000, okay, and then you increase it to, let's say, 5,000, then perhaps you may, the probability of you purchasing a house may actually increase quite a bit. So when you assume that it is a linear probability model, you assume that the marginal impact is the same, which is, for many cases, is unrealistic.